Hello, this is Mr. Stein, and in this video we are going to look at the example problems for section 5.5, graphs of relations and functions. By the end of this lesson, you should be able to write the domain and range of a function in set notation. Use the vertical line test to check if a relation is a function, and tell when data is continuous or discrete. All right, let's go to the example problems. Example 1. Which of these graphs represents a function? Justify your answer. So to test if a graph is a function, we do the vertical line test. We take each point of the domain and draw a vertical line through it, and if it only touches one range point each time, then it is a function. As you can see, this one here is a function. And in this one, we're going to do the masses of the students against the heights. So all we have to do is find one domain value that has two range values, and then it's not a function. So if we look here at 160 centimeters, we get two values. One value, two values. Therefore, this is not a function. There's a couple other places where a domain value has more than one range value, for instance, right here and right here. But all you need is one. And if you have one, then it is not a function. All right, we're going to talk about continuous versus discrete data. The question that we have is our domain continuous or discrete? So we have times on here. The question is, does every value on this domain graph, would it make sense to have a range value? In other words, we have a temperature here for 6 o'clock, but would it also be possible to have a temperature for 6:01? Would also be able to have a temperature for 6:01 and 10 seconds. It's asking us, would it make sense to draw a line here to indicate that there's a temperature at every point in time during the day? In this case, I would say yes, the in-between values would make sense. It would be possible to have in-between values. So in theory, this could be continuous data. But in reality, it's not, because we only have these exact data points. So because we only have these exact data points, this is a discrete graph. We only have data points for certain numbers. It could be continuous, because in-between values don't make sense, but in this case it's not. It's just discrete because we only have dots. Likewise, this one, it makes sense that it could be continuous because we could have all these different heights. Any in-between value height, we could have 161.53 centimeters, 167.585 centimeters, but our data itself is discrete. We only have certain ones. So while it could be continuous, our data itself is discrete. Determine the domain and range of the graph of each function. All right, so our first graph, we're going to start with the domain. The domain. I usually just put a D down for domain. The domain is our x value. So we always start domain like this, x. Now we look on our x-axis. How far left does x go? And then we take a look at where is x? X is all over there. Now if we look at the end of this graph, the end of this graph has nothing in it. There's no dot here. There's no dot here. There's nothing there. That means this line is going to keep going on forever. So this is going to keep going that way. So what is the largest possible value for x? It's 5. So our domain is all the x values such that x has to be less than or equal to 5. We put the equal to because it's got the dot there. And x could be any real number between them. This is continuous. It's a filled in line. Now let's take a look at our range. Range, we're looking up and down. We're looking on our y-axis. Here's our highest point at 2. And then our graph goes down. So our range is y such that y is less than or equal to 2, and y could be any real number that is less than or equal to 2. Because our graph has a highest point, our range is below the highest point. It's called the maximum point. All right, let's look at our second one. Again, let's do domain. Domain, we look on our x-axis. That's our farthest left point. That's our farthest right point. The domain is any point between these two. So it's all of our values of x such that -3, -3 is less than or equal to x. And we put the less than or equal to because it's a solid dot, which is less than or equal to 5. And because it's a continuous line, x could be any real number. Now let's do our range. Range is up and down. So we find our lowest point. Here's our lowest point. Here's our highest point. The range could be any number between that. So range is our y values such that 3 is less than or equal to y, which is less than or equal to 7. And y could be any real number. So for range, you're looking up and down. What's the highest point? What's the lowest point? For domain, you're looking left and right. What's the farthest left point? What's the farthest right point? Let's take a look at example number 3. The graph shows the approximate height of the tide in AH meters as a function of time at Port Clements, Heidig, Y on June 17, 2009. Identify the dependent and independent variable. Well, it's pretty easy. The dependent variable is right here. This is dependent. The height of the tide depends on what time it is. The time of the day doesn't depend on what height it is. The height of the tide depends on what time of the day it is. So R, for letter A, our dependent variable is H. That means our independent variable is T, time. You can see it right here. Time is our dependent variable. Letter B, why are the points on the graph connected? So at any point in time here, it makes sense that there would be a height of the tide. Right? At 9 o'clock, at 9:05, at 9:10, at 9:30, at any in-between values, it makes sense that there's a height. So the points of the graph are connected because it is continuous data. And I always use the phrase, in between values make sense. C, determine the domain and the range of the graph. All right, so let's take a look at the domain and the range. So letter C. Let's do the domain first. Domain, I'm doing that in green. We have data from 9 o'clock up to something up here. Well, let's figure out our scale. 10, 11, 12, 13, 14, 15, 16. This is 1600, which is 4 p.m. So our lowest value is 9 p.m. Our highest value is 1600. So domain. Our domain variable is time, such that 9 is our smallest time, and 1600 is our biggest time, and time could be any real number between the two. It's continuous data, so it's going to be a real number. Now let's look at the range, up and down. So we need to find our lowest value. Our lowest value is here. Now that looks to be about 0.9. Our highest value is here, 1.5. 1.2, this will be 1.4, 1.5, 0.9 to 1.5. So our range is all of our heights such that 0.9 is our lowest, and the height is bigger than that, and less than 1.5. And height could be any real number. So we've got our domain and our range, and we were able to determine if this was continuous or discrete data. All right, let's take a look at the last example, example number 4. Here is a graph of the function g of x equals 4x minus 3. It's a function because it passes the vertical line test. You should be able to see that quite quickly. Determine the range value when the domain value is 3. So our domain value, so for letter A, our domain value is 3. What is our range value? Well, we can do this on the graph. We look at our domain value of 3. We go up the graph to where it meets the graph, and then we determine our range value. And there it looks like our range value is 9. Or, since x is equal to 3, we can figure it out this way. Our range value, our function determined at 3, is equal to 4 times 3 minus 3. It's equal to 12, take away 3, is equal to 9. Determine the range value when the domain value is equal to 3 is the same as evaluating that function at x equals 3. Let's take a look at letter B. In this case, we don't know our domain value. We know that our range value is minus 7. So we're going to go into the graph. We're going to go to minus 7. So this is minus 4. This will be minus 6. Right here will be minus 7. We go across. It meets the graph right there, minus 7. We look up, and that'll be minus 1. So when our range value is minus 7, our domain value is minus 1. Now, we can figure this out the other way. We know that our function evaluated at some number is equal to minus 7. So we take our function, minus 7 is equal to 4x minus 3. Notice up here in the function, we eliminate that g of x and we replace it with the minus 7. And then we solve it. We add 3 to both sides to get minus 4 is equal to 4x, or x is equal to minus 1. All right, I hope